Hello, welcome you all to session 6 of Advanced Process Architecture. So, we have gone through the basic pipeline earlier, and then I have also covered quite a bit about how registers are organized in a processor and how instructions are structured and executed in an unpipelined CPU design. So, today we are going to discuss about how a pipeline RISC machine actually executes instructions. Okay, so I presume you are aware of basic digital design, which is more than enough to understand and follow this particular lecture. So before I start off saying simple RISC pipeline, I need to just mention what is RISC. As you are aware, it is a reduced instruction set computing. So there are basically two classes of processor architectures. One is RISC and the other one is CISC. CISC. One second, let me get my pen. So the other one is CISC. I do not have a backcom or any other tool now with me, so I am trying to write it using a mouse. CISC is complex instruction set computing, which came first, and then after the intensive research in the way instructions are organized and how they are processed in a processor, RISC came up as a popular way of implementing processor architectures. So let me just briefly talk about what is CISC and RISC, though I assume that you are already aware of it. CISC is a complex instruction set, as the name mentions. The instruction width could be varying, and the type of parameters, the operands in the assembly instruction, it is called operands. They could be either register or from memory, and it could perform a simple arithmetic or floating point or logical operations, or it could also do a very complex string compare or a string copy instructions operations. Okay, that is CISC instructions. The based on the kind of operation, the instruction width will be different and the structure of the instruction will be different. Whereas in RISC, the width of the instruction, when I say width of the instruction, means the number of bytes occupied by the assembly instruction when it is stored in the instruction memory. So that is fixed. Most of the time, based on the type of the processor, it could be a 32-bit processor, then you will have a 4-byte instruction width. If it is a very complex processor with more instructions, the width could be more. But the design philosophy is that the instruction width is same for all the instructions, and the way those operands are structured within the instruction, they are also fixed. So the advantage of RISC instruction is the decoding of instruction. That is, when the processor gets the instruction into the CPU, it will be able to understand what is that instruction supposed to do, and then try to make sure that the intended operations are performed by the instruction. So to do that, there should be a decoding of instruction needs to be done in the hardware at a very fast rate, the way the at the cycle rate in which these instructions have been read into the CPU. So we need to have a simpler structure so that it can be read, decoded, processed, and the results could be produced. So the intent of RISC is to simplify the implementation in the processor. Here I am going to explain the pipeline of a RISC processor. Okay, so not a CISC. We are not talking about this now. Now I assume you are aware of this kind of an assembly instruction. If not, I am giving you what is actually this instruction supposed to do. Normally the instructions are structured like this. The two operands that are required maybe for performing the operation comes here, and the destination where the result is supposed to be stored comes here. So it is like this. What is to be stored in R1? The sum of R2 plus R3, which is shown here. Now I'm going to show you a pipeline and I will explain you what are they. Before that, I want you to keep in mind that I am going to concentrate on only this instruction, the particular instruction which is shown here, going through the pipeline. Okay, let me explain what I mean by that. Now, this is a simple pipeline. Pipeline means as a normal pipeline where water flows through, this is a digital circuit, and in a structure like a sequentially arranged some digital logic to take in instruction from one end and then completing it and leaving those. Now, once the results are done, this instruction is ignored. It's not that this instruction goes out and saved somewhere. So instructions come in, and as per the instruction, what it is supposed to be doing is performed by the CPU architecture, and at the end of this, it will be completed. So that is why it's called a pipeline. Now, what are these? These are all different stages. You can assume it to be some walls in between different stages of the pipeline. I would literally call them as walls because what is happening here is independent of what is happening here. Because if I explain to you, when instruction is coming every CPU cycle, that means you know that there is a CPU cycle which is just a square wave pulse. So let me say that this is a one CPU cycle. Within this duration, one instruction is fetched from instruction memory. The IM is instruction memory. Now, one instruction is fetched. Assume that initially nothing is there inside the pipeline and everything is empty, in the sense there are no instructions occupying these stages. The CPU is starting off maybe on reset. You know that it is starting by fetching an instruction which is in a reset location. So it has not done anything before. So you can safely assume the pipeline will have nothing in those stages. So the first instruction comes in. Where is it coming from? It is coming from instruction memory. And then they go through different stages. I will explain what happens during the stages, but only thing what you should keep in mind that the transition happens during every CPU cycle. At the end of every CPU cycle, one instruction which is here fetched from memory transferred to this stage. At the same time, whatever is here is transferred to this stage. During the same cycle, this transition happens and also this. So that means they need to move in a lockstep manner. In the sense, at every cycle, the instruction what is in each of those stages should have completed in that location by that time, and they should have moved it to the next stage. You may wonder, will it happen always? It will not. In real life, it will not. One example is accessing a memory, data memory. If you want to access a data memory, if it is in the cache, which is, I'm assuming, a cache which is close to the CPU, it could happen in a single cycle. But you are not going to have the data always present in the data cache, so you may have cache misses. Then it will not be possible for this instruction, whichever is there, trying to write or read into the data memory, may not be completing within a cycle. In that case, don't think that this instruction will be just moved out even if it is halfway through. There will be hardware logic to understand whether this particular action is done or not, and then there will be an action taken which is called as stalling the pipeline. Stall, S-T-A-L-L. So that means no other instruction can come in until this is completed. So the basic summary of basic understanding that you should have is, on every cycle the instructions have to move from each stage, one stage to the other, and in case if one instruction takes more time, the remaining instructions behind will be stalled. That means they will not come and overwrite on the earlier instruction. Then when an action is taken, suppose when will you say, sorry, I'll start again. When will you say a particular instruction is completely executed? When it enters here, it is just read from the memory, and when it comes here, it has been completely executed. Then what happens during these stages? These are all the intermediate operations to be performed for achieving the goal of performing the complete execution of the instruction. Do you understand? We need to completely execute it, but we are splitting it into multiple operations and doing it in different stages. So what is this instruction pipeline achieving? We are trying to achieve performing different operations of the various instructions on different stages at the same time. So I will explain how this is achieved by showing you multiple instructions. Now let us understand one instruction. This is our focus is going to be on this instruction, not on other instruction which could have been there in the instruction pipeline in real life. So IF is a stage which is called instruction fetch. During the cycle CC1, the above instruction which is being read from the memory or a cache, instruction cache, is read and copied into this instruction pipeline. Let me now explain to you what are those pipeline registers. These are all called pipeline registers. Their names are, I will, as I proceed, I will share it with you. It actually has the names of the both the stages. This IF is instruction fetch and this is instruction decode. So this pipeline register, which is in between these two stages, is called IF/ID. What is the purpose of these registers? If you know digital design, if you want to store any computation or any value, anything that you have fetched from memory, you need to store it in a register, because these are all combinational circuits. As this input signal comes, it will perform some and or operations and then give out some binary outputs. So they do not have capability to store them. So we need basic a register, which is nothing but built using flip-flops. So since I said instructions go from one stage to the other stage, they need to be stored somewhere, because what instruction was here is moved, and whatever the operation needs to be done for the instruction, once it is moved here, it should be performed here. During that time, another instruction is coming here. So we need to pass on the information about this instruction which has been read through the pipeline registers, so that when the same instruction is coming through different stages, each of these logic, it's a combination of circuits, will know what is to be performed. So what we read, that instruction has the information about what is it expecting the CPU to do. That is stored in the instruction register. When we normally call it in a CPU, the instruction which is read is stored in the instruction register. In a pipeline implementation, we will be storing it in this pipeline register. So this information actually completely talks about what is to be performed by this instruction. That means it is telling each of those stages to do some part of this operation to finally achieve the goal of computing this and storing it in R1. So let me explain. Once I explain, you will be able to easily understand. So the instruction read has the information about it is stored here. One cycle is gone. During the next cycle, now we are supposed to do two things during this stage. That is, decode the instruction and understand what is it supposed to do. Here we just read the instruction from the memory. CPU does not know what it has read from the memory. It doesn't know which instruction has come in. It is understood during the decode stage. Then it knows that okay, it is supposed to perform addition. But this on this stage, it doesn't have any ALU, arithmetic logic unit, to perform this addition. It has a register set. It is shown here. A register set means all the registers which could happen, which could appear in an instruction is available here. They are all accessed during this stage. And this is dotted line is given shown here and solid line. There is a reason behind it. I will not explain now. So During this time, it is reading those two registers which are the operands for this instruction, R2 and R3. Now, as I told you, reading happens here, but it needs to be passed on to the next stage for really performing the addition. That means the value which has been read from R2, well, from register set, which is nothing but the values of R2 and R3, should be stored somewhere, whereas it has to be stored in the pipeline register. What is the name of this pipeline register? It is very simple. It is ID and ID/EX. So this is, before I go here, let me explain this. Assuming instruction cache is present, assume we are doing it in a cycle, we are reading it, and then in a decoding stage, as I mentioned, we are going to store it in this register, which is called ID/EX, which is holding the operands to be fed into the ALU. So ALU needs two input. They are coming from these two values. Okay. Now the instruction has moved. The next cycle, the third cycle, the instruction has come here, along with what it needs from the register set, the values. Now you may wonder, how does the ALU know it is supposed to perform an add operation on this operand? Or is it supposed to do an AND operation or a subtract operation? A good thought in the mind. That is understood when this decode stage, during the decode stage, it has been understood that it's an add operation. So there are some control signals generated is also passed across the different pipeline register, which is not shown here for simplicity's sake. Okay? Later we will see when we address those issues, we will talk about those things. Now our intent is to make this instruction go through. Now what happens on during the third cycle? It is going to get added. But remember one thing, during the same time, there are more instructions coming in from the pipe memory. Okay, I'm not talking about it, but you should have it in mind that it is not that the CPU is going to wait till this instruction finishes and then start fetching the next instruction. Then there is no use of pipeline. Pipeline is to perform multiple stages of operations on multiple instructions. Okay, so we are simultaneously doing it simultaneously. So we want to keep fetching instructions while one instruction is progressing, or not even one instruction, many instructions are progressing, going through different stages. So here our focus is on one instruction, so let us not, but you should keep in mind that there are some instructions following it which we are not showing. We are not interested in showing what is happening in those stages. So during the third stage, what happens? Execution happens. This is called CC3. Addition of the ALU, addition operation by ALU is performed and the result is returned. Where is it written? It is written in this EXMEM stage. Okay. So what is a memory stage? Memory stage is for storing any data into the data memory. Remember, this is also memory, this is also memory. This is an instruction memory which only stores the instructions which are required to be executed. Whereas data memory stores your variables, what you have defined in your high level programs, they are all stored here. So there are some instructions which stores some values which our computation is performed by the CPU into data memory. We may do it for storing or loading some values from the data memory into some registers. Now you may wonder, we are performing only add operation, there is no memory content here, then why are we going through this stage? The fact that this particular stage is reserved for my memory access, every instruction going through needs to spend some time, a cycle on this, whether it needs to access the memory or not, because it is in the pipeline. Whether if a particular instruction needs a data memory operation, it will be done. I will show you some example. In this case, it is not required, so it will just perform add operation in the ALU stage. And what will happen during this stage? It just passes that value. One more thing, remember in RISC, we do not have operands coming directly from memory for arithmetic operation. We will not have one of the operands as memory operands. That's why it's called a simple reduced instruction set. So we are only having operands from registers, and in this particular case the result is also written into the register. Normally in all RISC processors, arithmetic operations or any logical operations have destination also as a register, need not be a memory. But it is not true with RISC processor. As you are aware, this is a RISC pipeline, so we don't have to worry about memory operands being in this instruction. Okay, I am just bringing out those things so that while you are reading, learning about RISC, you also know what is normally done in a RISC processor, a complex instruction set computing. So what happens during this stage? You might have guessed it now. The value which has been stored in this pipeline register is not yet written into R1. Please remember, it is not yet written into R1. I am coming to that. It is passing through a memory stage, whereas this instruction does not need any memory access, so it has to skip through. It should just pass through that particular stage. One cycle will be wasted during that time. So this value needs to be passed on to this pipeline register. That's naturally, you might have guessed it by now. So how does it happen? There is a connection between these two ends. The control signals coming will know that it is an add operation and the result needs to go to a register, and it has nothing to do with data memory. So there will be control path set so that this data goes to this pipeline stage and it gets latched onto this pipeline register. Now what has happened? This instruction has gone through the pipeline and the result is available here. What is the name of this pipeline register? Very simple, memory stage and write back stage. What is WB? Write back. What are you writing back? We are writing back the result of the instruction which was computed here. Now it is available in the pipeline register here. It's an input to this, and the value needs to be stored in a register. Register will be in the register set. So you see that during this time register set was accessed for reading purpose, and during this time the register set is accessed for writing purpose. But you might wonder that you may think that this is happening at different point in time. Maybe initially it was because only this instruction was there in the pipeline, only R2 R3 was read, and here nothing was there during that time. Now imagine, as I keep saying, that there are some instructions keep coming from the behind at the back. When this instruction is writing the result, during this time, this is one half of the cycle, first half of the cycle. At the same time, I'm sure you must be aware now that there is one instruction in the pipeline at this stage trying to read the operands it wants. It is not this R2 and R3. This R2 and R3 are already moved here. So some other instruction, it depends on what has come, which may be reading the register set for reading purpose. So remember, it is happening at the same time. So I will come and then explain to you in this same session how this happens. Okay, I'm just giving you some thought. Maybe if you don't follow, wait for some time, you will be able to understand. So let us bother about only this instruction. It is supposed to write back the result. Now how does it know it is supposed to write it to R1? That information is also passed between the pipeline registers. So it knows that it has to write the result which is available into R1. That's all. So we have successfully now seen an instruction getting executed through a RISC pipeline. So let me bring out some relevant points here. This picture will show you exactly what I meant in the previous slide. So let me call these instructions as I plus 1, I plus 2, I plus 3, I plus 4. They are all entering the pipeline at different cycles. Okay. Every one after the other. Every cycle it enters. And they go through, shall we recall this? Instruction fetch, instruction decode, execute stage, memory operations, and write back. So let me show you the same add instruction coming in. You know what would have happened when it goes through it. Okay. Now let us see. I am just assuming there is one more instruction which is I plus 3 is coming in, which is nothing but R3 plus R5 into R6. It is going to R6. Now look at this. I have colored it differently. The same register R3 which is getting the result from this instruction is an operand here. Okay, is an input operand for this instruction which is coming in later. Understand that this is in time. If I have to draw the timeline, it will be like this. This is first, after this next cycle this, then next cycle this, next cycle. So instructions are fetched in this order. Timeline is this, going downwards. Now based on the instruction, the stages will be like this. This instruction is going through different stages. When this comes in, it is in IF, ID, EX. Now what is this stage and what is this stage? They are the same hardware. Remember, they are the same hardware. It is shown in this way only to show you that when these different instructions enter the pipeline, which are the stages they act on is shown here. So if you see here, let me just explain. On the first cycle, this will be here. The second cycle, this would have moved here, and this instruction will be here. And the third cycle, this would have moved here. At the same time, this is also moving, and third instruction comes in. And when this moves, this will move into ALU. So you can see that this instruction is following this I closely. It is one stage behind, whereas this instruction is two stages behind the first instruction. So this is how the instructions are coming in, and they go through the different pipeline stages. Now I showed you only this instruction and this instruction. What are these two? So for making our understanding simple, I am assuming it as a no op instruction. No op instruction means no operation. It doesn't have to perform any operation, but it will occupy the instruction stages. It will waste one cycle each on whenever it is occupying one stage, but they go through it. It is to simplify understanding of this particular thing. Okay, so let me now explain it. This is to explain how different instructions, when they go through the pipeline, what happens. This is to give you an idea of various instructions going through the pipeline. So no op is explained. Now this instruction is dependent on the result coming from this instruction, because it is to compute this R3, and after two instruction it is required to read that value, because either user has written an assembly program in this order, or a compiler has generated an assembly program like this. It is expecting a result which is nothing but R1 plus R2 stored in R3 is a parameter here which is to be added with R5 and stored in R6. So these two are dependent instructions. Now we have to see whether this instruction really gets the result or not. Let us understand it. Okay. Now if you recall, just in the previous slide I mentioned that this is the first half of the cycle. This is a cycle. This is the first half of the CPU cycle. What is happening? The register set is nothing but these registers. All the registers are called register set. The result of R1 plus R2 is written into R3 during this time. Okay. And if you see, this is a timeline. At the same time, what is happening on other stages. So during this time, at time, maybe if I call as time t, this is storing this value, this instruction during this write back stage. At the same time, no op is going through this memory stage, doesn't have any operation to do, it just goes through. During the same stage, no op, no operation done. But here I am given you a valid instruction which is supposed to read its operands. I told you, though we call this stage as instruction decode, it is performing two jobs. One is instruction decode as well as operand reading. It is reading the operands from the register set. So we need to read these operands, but one of these operands is expected to be the result of this instruction. Now my worry is whether it has been written or not. If you see that R3 is written into during this first half cycle, and during the second half only I said a reading happens. So that means R3 is expected to have been written and stabilized. The value is written into the flip-flops. Either it is a 32-bit processor, so 32-bit register. It is written and it is available for reading for this instruction during the same cycle. But it is happening just after the first half cycle. That means it is not happening exactly at the same time. It is here and it is reading is happening here, reading is happening here, writing is happening here. So it is at two point in time it is happening, though it is happening during the same cycle. So it has been structured this way so that even if there are instructions which are dependent on each other, they can get their parameters without any delay. In the later stages, I will talk about if I have this instruction here, how will it get the operand? That will be a different topic. I will not talk about it right now. Okay, so you understand that how a register set is read here after the writing is done. This is for the purpose of this instruction and this is for the purpose of this instruction. All these operations are happening at the same time. Okay, so I hope this is clear to you. Now a register set needs to have a multiple operations to be performed on it. We want to enable at least two reads to be performed. At the same time, one write needs to be performed. Maybe I am saying that it is after the cycle in the second half, but still it is in the same cycle. Why two reads? We need to maximum read two operands at least. So if you see during the same cycle, okay, reading is happening. Sorry, not here. I am showing it in a different place. Reading is happening here. How many operands are getting read? R3 and R5. So it is the same register set. So we are reading two reads we are performing on the register set. It need not be different registers. It could be same register also, no issues. So we are performing two reads and performing one write. All this can be same register and still it will be valid. So our register file is capable of performing two reads and one write in this particular architecture. I am assuming that it is capable of performing. That means what? The register set has been built with the necessary digital circuits to enable two operands to be read during the second half of the cycle and one operand or one result can be written into one of the registers during the first half of the cycle. So it has been already implemented in the hardware so that we can achieve what we want during the execution of instruction. So this clearly explains to you. Now I will talk about the implications of register file. As you are aware, the register file is used in two stages. This is what I am explaining you again. It is used. These uses are distinct. So the same register file is shown in both the places. Okay. Though we are showing two different places, it is all accessed using the same during the same cycle. One during the first half of the cycle reading and during the second half of the cycle first half of the cycle writing, write back. First half of it writing and second half is reading. So CPU may need to perform maximum two reads and one write. Both read and write can also happen to be the same register which I told you. And CPU performs a register write during the first half and reads two reads during the second half. So this has been explained already. So because of this capability, we are able to execute the instruction without any start because it is getting the operand it wants. So the instruction which is coming in is able to read the operands it wants, though the result is coming from the previous instruction. Okay. instruction stall means delaying the execution of instruction because it wants a result from some other instruction which is not available, or memory is not ready to give the data, so stall can happen, or some hardware is taking more time. It could happen in the floating point operations but not in integer operations. Okay, so I will talk about those things as when we discuss about those floating point operations later. One more thing, I did not talk about it previously. I said that the instruction is coming in every cycle. How can it come? Until otherwise, the instructions are accessed simultaneously, one after the other, in a consecutive, no, it's a consecutive addresses. Okay, remember, need not be simultaneous. What I mean by that is the instructions have to be fetched one after the other every cycle. That means we need to produce the addresses for accessing them on every cycle. So otherwise, if we do not update the address for accessing the memory, it may access the same instruction again and again, which is not what we want. We want the instruction to be accessed one after the other. Now we should know how many bytes an instruction occupies. I told you 4 bytes. In that case, if this is the address of one instruction which has come in, the next instruction will be at 104. That means what? I need to increment the address that I send it to the instruction memory by 4. Normally the register which is holding the address of instruction is PC. All of you may be aware of it, program counter. So because of the pipeline, every cycle I need to make sure the PC is incremented by 4. Otherwise it will not be ready for next instruction fetch cycle. So that is what I'm trying to explain. To start a new instruction during every CPU cycle in the IF stage, CPU must increment the PC by 4. I am assuming a 32-bit RISC processor, and store the new value into PC because it should also store it. It should be preserved in PC. So it has to happen in what? How much of time within a single cycle? So it's not possible if you are using this ALU for it. You are not even having access to that ALU during this time. So that means we are assuming some adder here, which is not shown. Adder circuit there, which is dedicated for only incrementing the PC and getting the new address ready for the next cycle. During the next cycle, we need to access it. So next address needs to be computed, stored in PC. So at this must be done during the IF stage. Furthermore, we must also have an additional adder, which I already explained. We will talk about branch later on. Okay, that is, it has to compute a new address. A branch will be there. I will explain it later. We may need an additional adder here, which is deferred for later discussion. Now, I'm sure you have understood what all the requirement. An instruction to go through a pipeline, we need the PC to be incremented at least every time by 4, and the register set needs to be stored as well as read from in the same cycle. I told you about the first half and second half of cycle. ALU performs the job of the instruction, add or subtract, and memory, I told it will be used if there is a requirement. I will talk about it now. Writeback is common for all. It has to store the result during the writeback stage. So what is this instruction? I am showing all ARM based instruction just for a uniformity sake. It's not a, just in case if you are aware of ARM, you might have seen this instruction earlier. So load instruction, what is this? This is R2 is a content of R2 is taken and a offset of 4 is added. So when I show you like this, it is something like value of R2 is taken, it is to be added with this value, which is a constant value. Normally it is a 16-bit value coming along with the instruction, or it could be different. It is stored along with the instruction. Now this constant, don't think that it is always positive, it can be negative also. So in all the microprocessors, we use 2's complement to represent negative values. I'm not going into the details. I expect that you know digital design. That means you know the representation of negative numbers. So offset could be a positive value or negative value. We can add it to the register content to generate the address. What is this address? Is it same as instruction address? No. It is a data memory. Is it? We are trying to access a data. Now, is it that we are accessing it for read purpose or write purpose? Are we reading from memory or writing into the memory? If you see, load is loading into a register. We are loading some value which is nothing but 32-bit value, because I am assuming a 32-bit RISC processor. All the registers are 32 bits wide. So I am accessing a memory, data memory. Address is generated by adding the value of R2, which could be a pointer, some pointing, an address pointing at the data memory. Already I am assuming that it is stored with the value. It is having the address. I am only adding a 4 to that, accessing the data memory, getting the content, which is again a 32-bit value coming from data memory and storing it in R5. That's all is to be done by this instruction. Now we'll quickly go through the pipeline, because now you are all aware how things go through. So instruction comes in, this instruction is coming in. I'm again assuming that only this instruction is flowing through the pipeline. Instruction register, that is decoding, not decoding, the content of the instruction, okay, which has the information about what is to be performed. Now immediate constant also is there along with the instruction. It has come within the cycle. Now decoding has happened. The CPU has understood that it is a data memory read operation to be performed during this time, and it needs some operands. What are those operands? It is R2 is an operand and 4 is as another operand. So in this case, so you see that R2 and 4 are access. R2 is accessed from here and 4 is coming from the instruction itself. It is loaded here. As I told you, the values are passed between the stages using the pipeline register. Now once this instruction comes here for the writing the value, it should know that R5 is the destination register. It will not have this information until it is passed between the stages. Remember that suddenly the CPU will not realize that what is to be stored is R5. It has to come from the instruction which came in first. So what is to be passed between the stages is also the information about R5. I am not showing it here. Okay. Now ALU is used during the execute stage for adding this value. Now before adding it, I told you that this is just a 16-bit value, but ALU is a 32-bit ALU. Now you need to perform a 32-bit addition. So this is sign extended. Okay. This is sign extended and added. You can read this content, what I am saying. Here sign extended 32-bit value is sign extended here and then loaded here, because we are doing it sign extension here itself, so that ALU is having all the 32-bit value which is shown here, and then ALU is performing the addition. Now what is this EA? EA is nothing but effective address. After the index offset is added with the base address is called effective address. You must be knowing this. So you have computed the address. Now we need to read from the memory at this address whatever is the content. So a memory read operation has to be performed. So previous instruction we saw, the add instruction, was not using the data memory at all, but I am showing you an instruction which uses the data memory here. So during this time, during CC4, data memory is accessed to get the value stored in the effective address, which has been computed by the previous stage. At the same time, remember, I plus 1 instruction is here, I plus 2 instruction is here, they have come in already. I plus 3 is being accessed. This is also accessed and this is also being accessed. This is the data memory, whereas this is an instruction memory. That means what? We assume during the same cycle, a data memory can be accessed and an instruction memory can also be accessed. You must be aware there are two ways an architecture can be defined. You may have data bus, address bus connecting to memory, either single interface to access both instruction and data memory, or two different interfaces to access them. If you have two different interfaces from the CPU to access the data memory and instruction memory, it's called Harvard architecture. So we assume if you want to implement, we assume pipeline, if you want to implement, we assume we need to have a Harvard architecture as well as instruction cache and data cache. Why? We want to access them within a single cycle so that all the instructions flow through it in a lockstep manner. Every cycle they move through. If suppose we don't have a cache, this will take more time. This will also take more time. Then none of the instructions can come out every cycle. They cannot execute in a sequence. See, why are we doing all this? Let me explain, though it has been covered earlier. The intent of pipeline is after 5 cycles are over, assume the pipeline was empty, and after 5 cycles are over, you will see that one instruction will get completed every cycle. Okay? So, with the help of doing different operations during the cycle, we are getting a benefit of completing every instruction, completing one instruction every cycle. So, if there are 5 stages, we will complete in a no one cycle, we'll get one instruction out. That means 5 instructions will be in different stages of execution. So that's what I'm trying to say. So in this case, what is happening? It is accessing the content of stored in the data memory at this address. Now at the end of data memory access, you will have the value. So always value is shown with the square bracket. That is a convention used in assembly instruction. So that's what is being stored is the value stored in this address. That's why a square bracket is shown. I am also showing here that it is a value in that address is now here. Here what is shown is the address. This pipeline register is having the contents that was there in this data memory read already now is available now. What is to be done? It has to be stored into R file, which is happening during the write back stage. And you know that it happens during the first half of the write cycle, CPU cycle. Okay. I hope now you have understood how this a particular memory operation is going through the pipeline. Now it's quick. I am going to be very fast. This is a quiz. I expect you to complete now how this instruction would go through this pipeline. You can pause this. If you don't know this instruction, what is it supposed to do? It's a store instruction. It's supposed to store value in R6 into the address. So I want you to pause for a minute, and then as you execute this instruction through the pipeline and write down the values on each pipeline register, what would have come in this pipeline registers when this instruction was going through the pipeline. I'm sure you should be able to do it. Okay, so pause it, do it now. Okay, welcome back. I hope you would have done it. So let me quickly explain the answer. I know instruction register, the content of the instruction. Now it has to have 3 parameters to be passed across, because I don't know whether you got it, you might have missed it, maybe if you are very alert you might have got it. So even if you have missed it, no issues, it happens, first time it happens. So R6 has to be stored into the memory. Now I need to access the value of R6 here for me to store it during the memory cycle. I cannot suddenly go here and access it. There is no provision. I don't have the access. The hardware circuit does not allow me. So R1 is read. This is coming from instruction, sign extended available, and R6, the content of R6, which was here, is accessed and put here. Now, what is passed on to ALU? Only these two values. We need to perform only this. So it will perform EA addition. It will perform the addition EA, which is nothing but R1 plus 8. And R6 is just passed as such without anything. That is why you see that there is something like this. It could be the direct line. Okay, don't bother. R6 comes here. And what is coming here? It is coming the address. Now, if you know, you must be aware, if you want to write something into the data memory, you need two things to be available with you before starting a write cycle. That means address, where you want to write something, and what you want to write, the data. Both should be available to you before you start the write cycle of the memory, which is available now. We have the values to be stored, value to be stored, and the address at which the value to be stored. So write it. Job is done in one cycle. Assume it is done. Okay, because I am assuming everything takes one cycle for explanation purpose. Okay, it need not be always true. What happens next? What is to be performed next in the write back stage? Nothing. You don't need to do anything because the job is done here. But as I told you, the instruction needs to spend cycle in a stage, because no other instruction can come just because the previous one has nothing to do. It's all already structured and it needs to be done like this. So it will spend nothing doing it doesn't do anything during this time. So I'm sure you might have got this now. I'm going to give you a simple exercise now. This was a little tough. So I will give you a simple instruction. I'm sure you know AND operation. What is to be ANDed? R7 and R8 to be bit arithmetic binary AND operation is performed, and the result needs to be stored into R6. I'm sure you should be able to come up with the values without any issue. So please pause here and continue. Welcome. You are ready? So let me quickly go through this. You will read R7, R8 from the register set. The ALU is capable of performing AND operation also. Only thing is it doesn't know whether it has to perform what operation. That is coming from here. So it is passed on. So no issues. You are making ALU to perform what you want. Do you have to do anything here? No. It's similar to whatever you saw in add instruction. So the result comes here directly and it is written into R6, which is here. So I'm pretty sure you might have now understood clearly how an instruction pipeline works. Okay, I'm going to give you a bigger quiz, little bigger quiz. It needs a lot of understanding of whatever you learned so far in the last maybe 45 minutes or 50 minutes. Whatever you learned so far, you can apply and answer these questions. So I'm assuming an instruction stored at address 100. I'm giving you address now. I want you to think as well as implement the theory that you learned in this quiz. This quiz will give you, if you do it well, everything correctly, you understood this class pretty well. Very simple. So I am saying the instruction is stored at 100. This instruction, I am assuming the pipeline is empty before, okay, to make our life simpler. Another instruction is this one, this loader. This is load instruction, this is store instruction. You know the syntax and what it is supposed to do, and a couple of other instructions. Now only this is new, but don't worry, it is nothing but a constant is coming along with the instruction which is to be stored in R11. That's all. It's a move instruction. It is moving a constant value which is coming along with the instruction to be stored into R11. You know that it has to be sign extended. Okay, this will be stored as a like an address offset. It will also be stored, immediate constant will also be stored as 16-bit value, or depends on the instruction format. Needs to be sign extended. You know which stage it is done and stored into R11. So assume, what I suggest is, once I give you the instruction, you will know what all things happen during these stages. You can write down, okay, and then answer my questions. My questions are this, too many, 9 questions. And I want you to answer this question assuming that the pipeline is at this time, okay, exactly time t. That means this CC5 cycle is also over. That means these instructions have already crossed some different stages and they are at this stage. So I want you to answer this question assuming that these instructions have spent some time. This is only just entering. This has spent two stages, it has gone through. This instruction has spent three cycles and it has crossed three stages. This has spent four cycles and this is the maximum. It has spent five cycles. Okay. So it's a little complex. If you get everything right, you can say whether I have done a good job or you have understood it well. It's both. It needs to be both. You will get everything right, but you may make mistakes and some you may not get some values correct, but it's okay. What is required is you have to choose all the correct options at time t, that is end of CC5. What are the options are correct? You have to say whether a particular statement that I make is true or false, and you have to choose only the true options. It doesn't matter. What you need to say is, okay, this is true, this is maybe false, this is true, this is false, something like that. Okay, what I want you to say is this. Please don't read by, try to get the answers from my what I said. They are completely wrong. Okay, I'll give you some time and you can pause this video and check whether you have got the answers correct. All the best. Okay, welcome back. Let me now explain. I hope all of you have answers in your paper. So what does it say? PC will be pointing at an address 120 when at this time t. This is the most easiest of all because PC, I told you already, is a program counter storing the address of the instruction and all the instruction with the 4 bytes I already told. Here I said that this instruction is at 100. That means what? I also told you PC plus 4 is done every cycle. So this instruction is at 104. This is at 108. This is 112. This is a decimal number. Okay. And this instruction is at 120. Sorry, let me read it again. 100. Okay. 104. 108. It is little tricky. Okay. 108. 112. Okay. 112. This is 116. Okay. This instruction is at 116. And what I told you during the instruction phase stage, it is incremented by 4 for the next cycle to access the next instruction. That means it should increment it by 4 because this instruction has already been fetched in the cycle. I am asking you the question at the end of this cycle CC5, that is at time t. That means it should have been updated by now for sure with the plus 4 value. That means 120 should be the value of PC at time t. So this is correct. Okay, A is correct. No read access to DM so far from any of these instructions. So this is a store instruction, writing it. So it is not a read operation. This is arithmetic logical operation. So it's not accessing the data memory at all. But this guy is a load operation. It's reading from the memory. I am saying no read access to DM so far. So far means till this point in time. So far from up to till this point, not here. Okay. Now I need to check whether this instruction has it initiated the data memory access. Okay, where will it do? In this stage it will do, but it will do only here. After time t, it will start the read operation. That means prior to that, this wouldn't have done a read operation. This also has not done, this also has not done, and I assume there is no instructions in the pipeline previously. Okay, that is also assume that pipeline was empty. That means no read operation, data memory read operation wouldn't have been initiated. So every statement is valid. You need to read everything to get the answer. If you are not very not even confident, very careful, may miss some point. So no read access. Yes, this is also true. This is also true. Let us go into this. Value in R1 has been stored into DM. I am making a statement. Let me see where R1 is used. Okay, it is used here. Okay, store operation. Okay, it's stored in data memory. It says that R1 is stored in data memory by this time, where this instruction would have stored the value. It would have stored it here, much ahead of this. Yes, so this is true. Instruction add R8, R9, R10. Where is it? Let us search it here. Is at the address 112 in the IM. Is it true? We calculated the value 100, 104, 108, 112. Yes, true. So it is there. That's why it was accessed. The pipeline register IDEX. Okay, this is a little tricky. You will not know where is it actually. IDEX has the value of R9, R10. A simplest way I have not explained. It's okay even if you have not understood or if you have made it out. It is really great. Otherwise, you might have missed this for sure. It's okay, no problem. Okay. I am saying IDEX has the value of R9 and R10 as operands. Now, which is IDEX at this time? There are so many pipeline registers here. See, this pipeline register is same as this pipeline register. This is same as this. This pipeline register is same. There is not two copies of them. There is only one, which is shown in two different places. You should know, because time wise, when we are showing the instruction execution, we are showing it like this. So they are same pipeline. Now you need to look for our friend IDEX. Where is it? You should know at this time which instruction is in the between ID and EX stage. I am right now pointing here. This is ID stage, instruction decode and operand read, and this is the EX stage. So this is the instruction register that we are talking about. And I am saying that has R9 and R10 as operand, because we need operands to be available here, which are, I am saying, I am making a statement, it is R9 and R10. Is it true? Of course, it is true. Yes. So this is also correct. Okay, so far everything is correct. Pipeline register IFID. Now you should be able to get it. See, even if you have not got anything wrong and I am explaining the answers for the remaining, you can pause now and try to re-look at your answers. Okay, you have still time. Don't think that you cannot change the answers. You can still do it. So IFID, you know where is it. This is the IF stage and this is the ID stage. This is the place. Very good. Now having the instruction move just read from IM. Of course, it is just read and it is passed the IR value. So this is also true. Very good. So three more to go. The result of R4 and R5. Where are R4 and R5? Yes, here. Where is the result? Just before the write back stage of this instruction. Write back is here. This is a pipeline which is between, this is memory and write back. So the result of R4 and R5 is available in the pipeline register mem/r write back. Of course, this result will be here. Then only you can store in the next cycle, you can store the value into R3. So luckily this is also true. Okay, two more. The only instruction which is fully completed by now is this one, which is nothing but the instruction I. It is true. This is the time. Only this is completed. I tell you, unless the instruction has exited the pipeline, you cannot call it as executed completely. Okay. So in our case, all the other instructions are something to do next. After this time t, they need to do something more. So they are not completed yet. So this statement is also true. One more. R11 was not accessed so far by any of these instructions. I am making a statement. Is it true or false? R11, no, 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 no. I'm not seeing anywhere. Oh, guy, it's here. Has, then it should have been read. Um, but don't jump to conclusion. My questions are a little bit tricky always. Sorry. So I am saying at this time, not after this time. Various statements are very accurate at this time t. So actual reading is going to happen here in CC6, that too during the read cycle, the second half of the cycle. During that time, R11, I'm sorry, it's a move instruction. In fact, it will not happen here also. I'm sorry. It will not happen there also because R11 is, it is supposed to store this value into R11, which will happen when this instruction comes to write back stage. It is still 4 cycles away. So R11 has never been accessed at all. Okay, before T. So all the options are correct. If any of you got this, all options are true. I can tell you, I'll give you a chocolate. If it was an online class or face-to-face class, I would have given a chocolate. Unfortunately, I'm not able to give you, but when I meet you, I will give. Okay, so I think if you have gone through this and followed this lecture, I'm sure you might have understood now completely what is happening in a pipeline. Okay, it was nice sharing this knowledge with you. See you next time. Bye bye. Have a nice day. Thank you. Thanks for your time.